Thank you. I'd like to start by saying that this meeting is being recorded. If anybody have any concerns of that, please let me know. Then I would like to acknowledge the traditional owners. I would like to begin by acknowledging that I'm hosting this meeting from the traditional lands of Wala Matugal people. I pay my respect to their elders, past and present, and I would like to extend this acknowledgement to all traditional owners of various lands on which each of you live and work. Hello everyone, my name is Jay. My pronounces are he/him. Today we have Robert Song, or he is visiting us from the Swinburne University. This just 1 second before I forgot something, Nikhil. This talk is also part of ASA ECR Symposium series, which will also be uploaded to their official channel. Okay. So Robert is gonna talk about. Sorry. Yeah. So Robert is gonna give a talk about gamma ray emission from nearby stellar flares and undetected pulsars. Before starting the talk, just a bit about Robert. So Robert completed his PhD at City University of New York and American Museum of Natural History before joining Swinburne University of Technology in Australia as a postgrad postdoc. His PhD research focused on developing stacking methods to observe faint undetected sources in gamma rays using Fermi. I'm hoping that you got it right. Fermi-led data. His current work focuses on population synthesis of pulsars using compass and body simulations of global clusters and detecting gamma ray emission from nearby flare stars. His pronouns are he/him. With that, I would like to request Robert to please start with your presentation.
Thanks, Jay, for the introduction, and thanks for having me here today. As Jay said, this is part of the ASA ECR Symposium series. I actually submitted 2 abstracts, and I was told I could do with any of them, and I didn't know which one to choose, so I combined the 2 abstracts. That's why you have 2 wildly different types of objects here today we're going to hear about. So I hope you find at least one of them interesting to you. So before I start, I would like to also acknowledge that part of my work has been done at Swinburne University of Technology. So I would like to pay my respect to the Wurundjeri people, which the Swinburne land is standing on, and I would like to pay my respect to their elders, past, present, and the future. I think the thing that ties together the 2 wildly different types of objects I'm going to talk about is the gamma ray emission. So I'm going to start by talking about gamma ray emission, how we observe gamma rays, how we do the data analysis, and the technique that I have used to observe both of these types of objects. Let's start with the Fermi Gamma Ray Space Telescope. The Fermi telescope was launched in 2008. So it started to work in August of that year, and there are 2 major instruments on board of the spacecraft. The first one is gamma ray burst monitor. So I don't use that instrument, so I'm not going to talk anything about it. But I assume if someone studies fast radio bursts and follow-ups, they might be interested in that. The instrument I use is the Large Area Telescope, or LAT for short. So it has 2 steradian field of view, which covers about 1/5 to 1/6 of the entire sky, which is, think about it, is quite large in the aperture. It can receive gamma ray photons between roughly 20 MeV to up to 1 TeV, and it surveys the gamma ray sky nonstop. Basically orbits the Earth in one orbit and flips around and look at the other side of the sky in the next orbit. So roughly goes through the entire sky every 3.5 hours. So that's been working since August 2008. That's over 15 years now. So we really have a lot of gamma ray data, and that would make it possible for us to study this large number of sources in gamma rays in full populations. So far, it has discovered over 7,000 sources. So that's like not a lot of number at all compared to something that Gaia would produce with 1 billion sources in there. But for gamma ray astronomy, this is actually quite a large number. If you compare it to the previous mission, which was EGRET, that has less than 200 sources. So very, very big step up from what we had before. And also another milestone for Fermi is that it received a total of 1 billion photons in 2020. Again, not like a bucket load of photons if you compare it to radio optical, where you point at something and you have, in a few seconds you get a very nice image. Again, it's a very big deal for gamma rays. So because gamma rays is that different from your conventional wavelength, I'm going to talk a little bit about the structure of the telescope first. So we call it a telescope, it actually behaves more like a particle detector, as you can see in this picture in the bottom right. What happens is that when we receive a gamma ray photon, it gets converted into a pair of positron and electron in the conversion foil. And these pair of particles then travel along the particle tracking detector, and then eventually they hit the calorimeter at the bottom of the detector. So this whole process would give us the time of arrival of the photon and the direction of the photon and the energy from the photon. So this kind of makes things a little bit complicated. So we got one photon each time, and we have to be really, really careful that which source or background this photon is coming from. So when we look at gamma ray data, we don't just simply say, "Oh, this looks like the Crab pulsar." So we say all of these photons coming from the Crab pulsar, and that's not it. We have to use maximum likelihood analysis to designate the photon to a source very carefully. This is especially important in complicated regions. For example, the center of the galaxy is extremely bright in gamma rays, and you can see it has an over of astonishingly 3,000 photons in this 14-year of data observed by Fermi. That is crazy bright in gamma rays. We want to be very, very careful if we're looking to that direction. Similarly, we want to be careful around gas clouds in the gas plane, which can cause a lot of noise. We want to also be very careful near bright sources, again, such as a Crab pulsar, which also has a pulsar with nebula around it, causing trouble if you want to observe something near it. And a lot of times, these bright sources, especially if they're AGN, they're variable. So that poses another level of whole complexity into this analysis. So how do we do the maximum likelihood analysis? We start by constructing the likelihood function first. So for the Fermi observation, the likelihood function is the product of the Poisson probability over all the pixels. The IJs are labeling all the pixels. The Poisson probability is telling us the probability of observing a certain amount of photon counts in that pixel compared to the modeled photon counts. And the modeled photon counts then contains all of the model parameters that we're interested in, including for each source, their coordinates and the gamma ray spectrum parameters, and for the backgrounds, their normalizations for the galactic diffuse background and the isotropic background. We're observing gamma rays. So, of course, taking the likelihood that we want to maximize the likelihood function, so it's going to be very hard if we have a product of hundreds or thousands of terms. What we do is we take the log of that function and turn the product into a summation. So what we essentially do then is to try to find the maximum of the local likelihood function and get that set of parameters as our best fit parameters. So by doing all of these, if we're specifically interested in a given source, we can then produce the test statistic of that source, which is given by twice the difference of of the maximum likelihood, which is the first term that you see there, the log of L. And that is that log likelihood function would contain the best fit parameters of the model, including that source we're interested in. And the second term is the log likelihood function value of the null hypothesis, which we have to remove the source from that modeling. So the rule of thumb is that when we have a TS value of about 25, that's roughly a 5 sigma detection in gamma ray. So we just take the square root of the TS value that tells us how significant the detection would be. There's more details into that. You have to take into the consideration of the degree of freedom and all of that, but yeah, generally, people would say 25 is good enough. I have tried to do stacking of gamma ray data with just photons, but this is that is just purely impossible because it's just too noisy and a lot of the sources are too faint. So what I ended up doing is to stack the likelihood of the sources. So just consider we have a population of sources, and when we want to look at the all of them together, we can just simply add up the TS values, and in turn becomes these big summation of a bunch of likelihoods, likelihood function values, and we can consider that. We can do some manipulations, consider there's some common null hypothesis, and turn this into the first term into a TS value of sources, and the second term into TS value of empty, supposedly empty control fields. That would give us a comparison between if the result is significant or good enough. I'm actually going to create a TS profile for each source instead of in the physical space. I'm going to look at them in the parameter space using the spectral parameters of the sources. So just to give you an example of what that would look like, I did this method on one pulsar. Specifically, when I started doing this pulsar was not detected by Fermi, but when I was near submission, they published a new catalog and said this is detected now, which is great. Now we can actually see if this is detection is real, which it is great. You can see that what I created is a TS value profile for the pulsar in parameter space. The horizontal axis is the gamma ray flux of the pulsar, and the vertical axis is the spectral index, power law index of the pulsar before it meets the cutoff energy. So what that means that if you look at I just realized the green doesn't work on this. What that means is that if you look at these curves on the right, which are the spectrum of this pulsar in gamma rays, there's very significant drop off of the flux after a certain photon energy. That is the cutoff, and this index is modeling the power law index before the cutoff. So basically we have what we have here is that the TS value of the pulsar in this parameter space peaks at the same almost exact the same value as what we can get from analyzing that Fermi detected source in the catalog, and the parameter also is the parameters. So the index and the gamma ray flux also roughly matches to those that are reported in the catalog. And because this is not a very significant pulsar in gamma rays, what the catalog did was to model it just with a simple power law, which is the pink line here with the pink uncertainty area. And if I just do if I take the parameters that I get from this, which is plotted in the green here, you can see there's some roughly overlaying the uncertainties. Because this is, again, not that significant. There's a lot of area in here that we are not quite sure. Because pulsars in gamma rays normally supposed to have a cutoff. We don't have enough photons from this pulsar to quite conclusively say yet what it's doing, which is why when you look at this blue line with the blue area that covers the bottom half of the plot, that's just to do the analysis of the gamma ray data with that power with exponential cutoff model, and it's wildly uncertain, as you can see. That's why the catalog publishes the parameter in power law. Anyway, so the stacking then happens when we have a whole bunch of these maps in parameter space. We just simply add the map, and we can then tell that as a population, these sources have a roughly common behavior in the spectral parameter space in gamma rays. So I have done this in a few different types of sources, and we had students do this in some other different types of sources. So today I'm going to talk about the flare stars and pulsars. One of the master students that I was working with when I was doing my PhD, he looked at global clusters using this method, and I think he's getting ready to submit his paper sometime in the next few months. And there are also some summer students that look at O and B stars and interacting binaries, but those are not in the list of things I'm going to talk about today. So I'm going to start with pulsars. So pulsars are this cosmic lighthouse, as you can see here in this diagram on the left. They spin extremely fast, and then they have this narrowly beamed emissions coming out of the polar areas. If you look at them in radio, and with their rapid spinning and the misalignment of the magnetic field, you can see this beam being brought back to you with each rotation. That gives you the pulsation that you see coming from the pulsars. They are highly magnetized, fast-rotating neutron stars. They were first detected in radio in 1967, and the first gamma ray pulsar was detected in 1974. So far, there are over 3,000 pulsars identified across the sky. I think some people online or in the room might be very familiar with the work that put into constructing this catalog. And the most recent catalog of gamma ray pulsars published earlier this year detected 294 pulsars in gamma rays. So now that's the first motivation of why I wanted to look at pulsars with these stacking methods in gamma rays, is because there are a lot more pulsars in the sky, and only a very small fraction of them are emitting in gamma rays. So do the rest of them are too faint to be observed in gamma rays, or do they not emit gamma rays at all? There are people arguing with that in both directions. So I thought this might put some perspective into which is more likely. Pulsars electromagnetic emission is powered by spin down. So what that means is that when most of the pulsars that we observe, their rotation is slowly being slowed down. That makes sense. Yeah, their rotation slows down throughout the course of time. That means that their rotational energy is being lost, and that is actually being transferred into the electromagnetic emission that we see. And their emission mechanism is still quite, well, I wouldn't say quite unsure, but it's still somewhat unsure, that people are having a lot of arguments. But essentially what is happening is that people more or less agree the radio emission from pulsar come from these polar cap areas that is aligned with the magnetic axis of the pulsar. So this is labeled by the B vector, and the omega vector is labeled as the rotational axis of the pulsar. It is, however, not so sure where the gamma emission comes from. What happens there is people think the energetic particles are accelerated by strong fields near the surface of pulsar, in these gap areas that are within the light cylinder, which is the distance to the pulsar surface where the rotation speed is the speed of light. And the acceleration fields would get screened off around the top part of the gap as the density of the particles increase. But there are also people saying that the acceleration actually happens around the light cylinder, where magnetic reconnection can propel a lot of the particles into relativistic speeds, and these particles then create these current sheets that can generate the gamma rays. Anyway, again, there are a lot more people online or in the room that are more qualified than I am to answer the exact nature of pulsar gamma emission, but this is just a quick overview of what is happening or what people think it is. So one way to examine pulsar population is to look at this what we call PP dot diagram. So for those not familiar with it, the PP dot diagram plots the spin period of the pulsar at the horizontal axis, and the P dot, the period derivative of the pulsar, in the y-axis. So you can see that there are, if we just look at the gray dots on this plot, if you can see them, these are all of the pulsars that have been observed, and we can see that they are roughly broken down into two populations. We have our regular or normal pulsars, or slow pulsars, or we say slow, but there's massive things that spin every second or every 10 seconds is still quite crazy, I think. And there's this other population of pulsars that we call millisecond pulsars. So their spin periods are closer to 1 millisecond, which is even crazier. Then I plotted these blue dots, which are the pulsars that are discovered or detected in gamma rays by Fermi. And you can see that compared to the majority of the gray dots, these blue dots mostly reside on this one particular side of a diagonal line of this plot. So this diagonal line, if you can read these diagonal lines with a larger slope, these are labeled with something with luminosity units per seconds. That's what we call the spin down luminosity of pulsars. So that basically is estimated to be the rate of pulsars losing their rotational energy based on their period derivative of P dot. I'll be calling the period derivative of P dot from now on, just to save some time. And their moment of inertia. So as you can see, these gamma ray detected pulsars in general seem to have a larger larger spin down luminosity, or E dot in general, which we can also see that here in this plot histogram on the right. Again, the gray are all of the pulsars detected, and blue are Fermi detected pulsars. We can see that the majority of the Fermi detected pulsars seem to reside on one side of a very sharp cutoff, and so some people call that the gamma ray deadline of pulsars. So people used to think that pulsar gamma ray emission gets turned off below this deadline, but now we're seeing a couple of pulsars that are detected with lower E dot. So it's quite interesting to see that, to find out if we can find more pulsars in this region, and also if they're actually emitting gamma rays. So the green dots we see here are the pulsars that I'm stacking. So actually, I did not deliberately chose lower E dot pulsars to study, but I actually chose these pulsars because they are away from the galactic plane. Because as I was saying earlier, the Milky Way galaxy is quite a strong gamma ray emitter, and it has a lot of interference and creates a lot of noise. So I want to stay clear of that. So I chose gamma pulsars that have galactic latitude larger than 20 degrees. And that actually accidentally give me older population of pulsars that have been kicked out of the galactic plane during their supernova explosion or whatever event that disrupted their orbit around the galactic center. And in turn, they, if you can again see these lines with diagonal lines with lower slopes, they are labeled with time unit, that is the characteristic age of pulsar. And you can see that these green dots in general have larger characteristic ages compared to those that are already detected in gamma rays. So we're seeing this population, trying to see this older population of pulsars. Yeah, so taking this sample, run through the pipeline, and bim bam boom, we have this. Yeah, so on the left, we have the stacked TS profile of all of the 360 pulsars that we just saw earlier. We have very nice peak here. We have relatively hard spectral index before the cutoff. That is generally characteristic to gamma ray pulsars. And when we look at a whole bunch of supposedly empty fields that are not near any Fermi sources and that have the same spatial distribution as our pulsars, we have this other peak. But we can see that this is actually consistent with the gamma ray background that is observed by Fermi. So basically, we're looking at the background here if we're just looking at the controls. Which means great. We have this signal coming from this whole group of pulsars, even though they're unresolved, they're working as a whole bunch of population. We still can say that maybe these pulsars are indeed emitting gamma rays, which is can't see them yet. So one way to put that into perspective is to look at this plot where we plot gamma ray luminosity of pulsars versus their spin down luminosity. The reason I do this is that people have found out that for the Fermi detected pulsars, which are again the blue points here, they seem to have a correlation between their gamma ray luminosity and their spin down luminosity. So people call this the heuristic relation. There are some pulsars here that don't really observe energy conservation laws. We don't know why, but it's most likely the distance measurement is not so great on these pulsars. It also might be due to the emission geometry. We don't have a good idea yet. But in general, we can see that for the majority of pulsars that are detected by Fermi roughly follows these gamma ray luminosity proportional to square root of E dot heuristic relation. These three green data points with horrendous error bars on them, they are the estimated luminosity of the pulsars that we just looked at. If we estimate if we bin them into different E dot bins first, and then estimate their luminosity using their spectral parameters out of these plots, and then we can again have that with horrible error bars that are also caused by the uncertainty in the distances of these pulsars. So again, it seems like combining these lower E dot Fermi detected pulsars, and what we are seeing here is that it seems like these low E dot pulsars are doing something in gamma rays after all. What is it? We don't really know, because the majority of gamma ray pulsar emission theories seem to still think that at some point in the E dot distribution, the emission mechanism should turn off. So we don't really know what it is, but it is possible that we have some unpulsed isotropic gamma ray emission coming out of these pulsars. and some people might disagree, and that is fine. Again, we don't really know what it is. We want to explore it. So here I go of exploring with population synthesis tools. Before I go on too much of this, I want to just say that the population synthesis is done with COMPASS. So COMPASS stands for Compact Object Merger, Population Astrophysics and Statistics. So it was originally developed to look at a gravitational wave population. But of course, neutron star is a type of compact object, and COMPASS produces that. So it is actually a great tool to use this kind of population synthesis tool to look at pulsar populations. It's based on COMPASS is based on the single star evolution code SSE and binary star evolution code BSE. They are predetermined descriptions of how stars would evolve given their mass. So basically, we don't have to run stellar evolution model each time we simulate a star or a binary system. We can just use that prescription and very quickly generate a large number of stars using this method. And COMPASS added a lot of additional things, including most importantly, actually, how the post-main sequence physics would impact the observed population of black holes and neutron stars. For my simulation, I used stars that have 5 to 150 solar masses. Any lower than that, we know that they don't really produce a neutron star at the end of their lifetime. And I used solar metallicity, and I'll explain why in the next slide. So each simulation I run has 300,000 systems. The orbital properties are predetermined, not predetermined, are the standard COMPASS set. So we have distribution of eccentricity and orbital period of the initial binary that we observe. Sorry, I should say that all of the pulsars I generate here are out of binary systems. And there's also a lot of command law properties that go into it, which actually don't matter much. And I'll also tell you why in just a little bit. And of course, actually a more important one is the supernova and the key properties that would tell us if the neutron star will still be bound in the binary or it will be disrupted, and other remnant prescription, including the mass and other distributions of the objects that we're interested in. We have to assume distributions of pulsar properties at birth as well. So that includes the distribution of period, which I set to be a Gaussian distribution with a mean of 75 milliseconds and 25 millisecond standard deviation, and the magnetic field is set to be a uniform distribution ranging from 10 to 11 Gauss to 10 to 13 Gauss, and a magnetic field decay timescale of 500 million years, which is more or less actually constant. This is how a rough cartoon of how the process goes. So we set birth time of the binary system when they're born, because COMPASS starts each binary system at the time of 0. We have to manually assign birth time. We let it evolve, and the more massive star becomes a supernova. And in some cases, it disrupts the binary, and we're only left with a pulsar, and the secondary can just go somewhere else, wherever they want to go. And the pulsar would slowly spin down if it doesn't encounter another companion. We assume that is the case until it loses the majority of its energy and we can't observe it in any wavelength anymore. But before that, we make an observation at the current age of the Milky Way galaxy and say that, we can determine from the output of COMPASS that the period of the pulsar is this and this, the field is this, the mass is this, so we can then estimate the other properties of the pulsar, including p dot, e dot, moment of inertia, gamma emission, radio emission, and all of that. Of course, we have to have a realistic model of the galaxy. So we again are assuming that massive stars forming the neutron stars, the massive star are born in a thin disk around the Milky Way. So let's assume that somewhere here in the galaxy, the binary system is born, and it just goes around the Milky Way, doing its own thing until it goes supernovae. Until it goes supernova, it receives a kick, so it becomes a pulsar and moves along the galaxy, following the kick distribution and the potential of the Milky Way, and then moves to somewhere when we make the observation in radio and gamma ray. So the selection effect in radio is based on, it should be 2014 or 2018, is based on this Zari et al. 2014 work. They basically have found that for the radio emission of the radio luminosity of the pulsar doesn't really depend on any parameters of the pulsar itself. It's more or less a log normal distribution. And the gamma ray luminosity we set as a correlation between the E dot, the magnetic field, and possibly the cutoff energy in the spectral gamma ray spectrum of the pulsar, which is called the fundamental plane by the authors. So as you can see, the gamma ray emission here actually follows tightly correlation between these quantities. For the radio observation of the pulsar, we assume that it is observed by the Parkes multi-beam pulsar survey, and that is realized by a package called PSR evolve. And for the gamma ray selection, we just assume the pulsar must be over the Fermi-Lat sensitivity, which is provided by the Fermi collaboration. And we also consider the beaming of the pulsars, and if they are beamed away from the Earth, we don't observe them. The result is like this. So we firstly look at the number of, I should say that we're only simulating slow pulsars here, because there's some issues with generating millisecond pulsars in COMPASS at the moment. So we'll fix that and do millisecond pulsar later. But for now, when we look at these slow pulsars, the PV dot diagram seems to match well between the simulation and the catalog, and we also have a roughly comparable number of pulsars in each category. And if you remember, I said we have 300,000 binary systems generated to generate these pulsars, and that actually roughly transformed to 1.2 solar mass per year star formation rate in the Milky Way, and the distribution of some of the properties of the pulsars agree nicely between the observation and the gamma ray. So, observation and the simulation. So, as I was saying that we were trying to understand what happens with the emission. So, in the first plot, we assume the observing conservation of energy. We assume that the pulsars follow some correlation between the luminosity and the E dot, and the result is in the from the simulation is in the orange dots. And if we assume some isotropic non-beamed emission, then it's in the second plot. If we combine them, it's in the third plot. Again, because of these horrendous error bars, we can't really say too much more about it. But when we look at the spectrum of these pulsars, with the blue being the data, this orange being the correlation of gamma ray luminosity and E dot, and the blue and the red being the isotropic, we can see that they also don't agree, but it might be just a mixture of the two that we are observing here. Again, because the quality of the data we have, we can't really say a lot about it. And there are still a lot of things to be done. And you can see that I have a full page of follow-ups. We're conducting a hierarchical Bayesian analysis on the stacked pulsars to try to get a sense of what's the distribution of the property is like on those stacked pulsars, and we want to search for off-peak emission from this from the detected gamma ray pulsars to see if there's any actual signal, if it's universal, weak, and isotropic. And also, we want to include millisecond pulsars in our study, which will allow us to do a study on X-ray binaries and continuous wave as well. And we can also use the compass millisecond pulsar results and n-body simulation results to look at millisecond pulsar population and explain the galactic center GeV axis. And there's magnetar, FRB, and other merger events. And I don't know if I have enough time to go on. Strict 45 minutes.
Keep going. There's a couple of more minutes.
Yeah, okay. Yeah, because I do want to touch on the flare stars a little bit. This will be quick. The reason I want to study the flare star is that the sun flares a lot, and it's observed a lot in gamma rays. But the sun's flare is not that energetic compared to these low mass stars. These low mass stars are throwing out flares 3 to 5 orders of magnitude more energetic than the solar flares. And some of them are, I don't know if you follow this, but a few years ago, there was a naked eye super flare coming off Proxima Centauri that was roughly 6 magnitude. Could be observed by human eyes if you have really eyesight in a really dark place, and they flare really frequently. And again, these high energy of flares, they might just be visible through the stacking methods to be observed in gamma rays. And another thing I'm interested in is that because these flares give out a lot of radiation, and these are accompanied by a lot of energetic particles associated with the coronal mass ejections, it can impact the habitability of nearby planets. So rushing through this, the first thing I did was to do a temporal analysis of a very well-known radio periodic flare stars, and we were able to detect a 4 sigma signal coming out of the star that has a period that is consistent with the optical and radio period. And I also observed with the stacking methods optical flaring stars and X-ray flaring stars from these 3 different catalogs, which you can see again that with the flare frequency distribution, the black line here is for the sun, and these other lines are for the star from our sample. They have much larger energies and they flare much more frequently, as I was saying before. The difference with this analysis is that we actually only look at the Fermi data around the flares instead of the entire observation length of Fermi. We only were able to get a very weak, upper limit, detection, but it's actually a strong-ish upper limit out of the flares, and the control gives completely empty detection. So we compared these to observe solar gamma ray flares, which is what the histogram here you're looking at is the power law index of the solar some of the solar flares from the Fermi observed solar flares. And we can see that distribution of the solar flare gamma ray index is similar to roughly corresponds to the signal that we have here. This is roughly a 3 sigma upper limit. If we compare the gamma ray flux of the solar flares to the flare energy output of the solar flares, there's somewhat rough, very rough correlation between them, if you believe there's correlation or not. And that is what our upper limit would place on the place us on the on this scheme if we believe that the solar this violent stellar flares and solar flares have similar mechanism. I'm going to skip through this, and so there's also follow-ups planned. I'm going to develop some more effective temporal analysis methods for other periodic flare stars, and we have a summer student from Melbourne Uni to include more ASCAP observed flares into the stack, and hopefully that can give us a better constraint. And I again want to try to see if I can find the implication of these flares on the exoplanet atmosphere and their habitability. And if you have any suggestions on that, please let me know, because I'm not an expert on that at all, and I'm really, really interested in it, and hope somebody can point me to a good start of it. Yeah, I'll just leave you.
Thank you, Robert. Really nice talk. Okay, so I'm opening floor for questions, comments, suggestions. Anyone online? Oh, somebody has their hand raised up.
Hi, Jay, can you hear me?
Yeah, we can hear you.
Yeah, so I have one confusion. So you showed one upper limit for stack, like for the flare star gamma ray flux, you showed an upper limit, and you also showed 1,4 sigma detection. So I'm a bit confused. Was that a detection of gamma ray flux during an optical flare, or?
Let me see if I understand that correctly. You're asking if this detection is based on the observation of optical flare?
Yeah, I mean, is the detection like occur during an optical flare? Like, does it coincide with an optical flare? That's my first question.
Oh, I see what you mean. So, yeah, this peak is in phase with the optical pulses from this star. So when the optical flare happens, the gamma ray flare also happens, but it's actually out of phase with the radio flare. So half a rotation later, we see the radio pulsation coming out of this flood star. Is that what you're asking?
Yeah. So basically, this coincides with the optical flare, but doesn't coincide with the radio pulses. Is that?
That's correct. Yes.
Okay. Can I ask a different question?
Yeah, sure. Go ahead.
So I'm just curious. What's the mechanism for production of gamma rays by these Luma stars?
Yep, that's what I skipped through. Yeah, basically, the quick scenario is that ejection from the flares produce energetic particles. It travels along the loop and comes back down to the stellar atmosphere and heat. And these relativist protons heat the protons inside the stellar atmosphere, and that creates neutral pions that decay into gamma rays. So actually, Fermi is the perfect instrument for this, because the peak of the neutral pion decay gamma ray emission is peaked at a GeV, which is essentially the best energy for Fermi to observe.
Okay, I have one more follow-up question, but maybe I'll ask you later. Yeah.
Yeah, we'll come back to you later. Rom has got some questions.
Okay, could you put up your plot where you showed the stacked detections of the pulsars gamma rays?
Yep.
No, the one with this, where you had the 3 stacked detections.
Oh, in this one?
Yeah, that'll do. Okay, now the process of stacking is forming the average of all the undetected pulsars in that particular bin.
Yeah.
Average makes sense when you have Gaussian distributions. It is a well-defined quantity. But the undetected gamma ray flux from these things is very unlikely to have a Gaussian distribution. So you have to think about what the detection means. And if you think about it, it tends to be the result of the small number of extreme objects near your detection limit. So it is a property of this stacking process that you get detections almost by definition just below the previous detection limit. because you've thrown out all the detected ones, and that's where the next one comes in. So that means the actual value, and the reason why the three green stripes have the same value, they're just telling you the detection limit. They're not actually telling you the average gamma ray flux from those objects.
Yeah, that's a very valid point. That's why we want to do this hierarchical Bayesian analysis to see if we can actually extract more information out of the, let's say, just the individual profiles of each of these pulsars instead of just looking at them as a whole. We're hoping that will give us more accurate result instead of we just, we're gonna have something near the detection limit and
In the process of doing this, you might make comment in your paper, almost everyone gets this, not wrong, but it's misleading. And everybody who stacks is doing the same thing. So if you develop a better way of analyzing this data than stacking and averaging, that's interesting for a broader community.
Good. Any more questions in-house? Yep, please.
I was just going to ask about so the idea of the isotropic gamma ray emission from the pulsar. So what's the origin of that?
inverse Compton scattering.
So, but from
So the photons should be from the pulsar's surface,
yeah,
which is high temperature.
it's just a hot neutron star.
It's just hot neutron star scattering of the
Stuff.
particles.
Yeah. Okay. I mean,
We've had arguments with a lot of people if this is true, but very quick modeling that we did seem to suggest that it's not unphysical, but whether if it's actually it, we're not sure. Yeah, that's why we also want to do more searches to see if it's like indeed what we think it is, or if it's some extension of the gaps that are behaving differently for lower Etoff pulsars.
The physics gets pretty weird at the velocity of light cylinder surface. Are any of the models trying to see what happens there? Is that a possible source? Most people don't do it because it's too hard.
I know one group that's doing that out of Flatiron. I haven't checked with them in a while, so I don't know their most up-to-date results on that.
Good. We can go back to the online participants. Someone got more questions?
Yeah, I have one
Yeah,
follow-up.
go ahead.
So, regarding the process in by which the Roma stars are believed to produce a gamma rays, so the same mechanism like electrons following the field lines and hitting the surface and giving rise to this possibly gamma rays and so that was also proposed for magnetic OBA stars. So I was wondering if Fermi has observed some of the magnetic hotter stars and if there is any update about the magnetic OBA star regarding their gamma ray possibility of gamma ray emission from them.
So let me see if I got it correct. You're asking if some of the OB stars that are also magnetically active have been observed by Fermi.
Yeah, if there is any observation and result. Yeah, that's it.
I know one group out of Brazil that have been working on observing OB stars, but I don't think they're saying their observation is based on the magnetic strength of those stars. They're just looking at the inverse Compton halo around those luminous stars because they're quite bright and the cosmic ray can scatter off the can scatter with the photon field of the star to create gamma rays. They haven't made any detections yet. Yeah, so I'm hoping that partially answer your questions because I really don't know if any of the magnetic OB stars have been observed in Fermi.
Okay, thank you.
Good. We got time for one more questions. Does anybody have any other comments, questions, suggestions? Okay, then let's thank Robert again. Thank you so much.